So we have discussed about generalized Hooke's law and problems related to generalized Hooke's law. Then problems on finding the change in volume when a rectangular block is subjected to stresses in all the three directions, and also elongations in the three mutually perpendicular directions. All those problems we have done discussed in the last class. Now today, very important concept called simple shear or pure shear. So sometimes a block is subjected to only shear force. It is not subjected to any tensile or compressive force. Now, as of now, you know the difference between normal force and shear force. Normal force is the one which acts perpendicular to the cross section. It can be tensile or compressive. Normal force is also called as direct force, and the corresponding stresses developed due to those normal forces are known as normal stresses or direct stresses. Tensile and compressive, they are the types of normal stresses. There is one more type of force called shear force, I explained on that day, which acts parallel to the area or tangential to the area. See here, you can see here, I have taken a block, maybe rectangular or cube, no problem. So you can see I have shown a force F here on the upper area. So this force is not acting perpendicular to this area, it is acting parallel to the area, or it is acting tangential to the area. That is why shear force is also called as tangential force. So here, when you can observe here is that this block is subjected to only shear forces. It is not subjected to any normal force, that is tensile and compressive force. You can see here I have shown one shear force like this and another like this upward. Then here one like this and another downward like this. Always shear force acts in this fashion. The reason is the block should be in equilibrium. So if you are applying a shear force on the upper face like this towards right direction, definitely there should be a shear force acting on the downward face in the opposite direction. So you can observe that this F and F, they are in equilibrium. Only effect of this F and F is they will create a couple. So you know about the couple. In your mechanics you have studied about couple. Two equal parallel opposite forces will constitute a couple. So here these two are equal forces, parallel forces, and also the directions are opposite. So the effect of these two is to rotate this block in the clockwise direction like this. Similarly, to keep the block in equilibrium, I have to take another two shear forces, one acting like this, another acting on the like this. That means in the left and right face, they are also equal, parallel, but opposite in direction. These two shear forces, if you observe, they will create an anti-clockwise couple. See here, like this, anti-clockwise couple. So top and bottom shear forces, they create a clockwise couple, and left and right side shear forces, they create an anti-clockwise couple. They are equal. So these two will be equal. So that means, so that the block will be in equilibrium. So that means what I want to say is, whenever there is a force, shear force acting on one of the areas like this, definitely there will be a shear force acting on the opposite face of same magnitude but in opposite direction. So that the entire block is in equilibrium. So that is the meaning. So due to the shear force F, there develops a shear stress. What is that shear stress? Tau. I have written here tau. So tau is defined as the shear stress, which is the ratio of shear force to shear strain. Stress. This tau is nothing but shear force divided by the area over which it is acting. So on that day, I told you about the definition of shear stress and shear strain in the earlier class. Shear stress is the ratio of shear force divided by the area over which it is acting. For example, here if I take this area of this face, so this F divided by this area of this face will give the shear stress. Newton per mm square will be the unit. And due to this force, there will be a distortion in this direction. So that is written as shear strain. I will come to that later. So now the state of simple shear or pure shear means when a block is subjected, when an object is subjected to only shear force or tangential force without any normal forces, then it is called as simple shear or pure shear. So in that case, these two conditions are satisfied. See, sigma h0, sigma v0, that is some of the forces, horizontal forces, that is this and this, they will nullify, and vertical also they will nullify. So equilibrium condition is automatically satisfied in the case of simple shear or pure shear. So if a material is subjected to only shear force, such a state is called as pure shear or simple shear state. There is no tensile or compressive forces acting. Okay. Tau is called as the shear stress, which is nothing but the ratio of shear force divided by the area over which that force is acting. Now let us prove that shear stresses always act as complementary shear stress and are equal to each other in magnitude. So that's what I told. So whenever shear force acts like this, there develops another shear stress which acts in the opposite direction. So let us take that I will take the same block. A is the dimension of this block, this edge A. B is this. Let us say this rectangular block with edges A and B. A and B, rectangular block. Let the thickness is 1 unit. So let me take the thickness. This is the thickness, CC dash or DD dash or BB dash or AA dash. This I will take it as the thickness. Thickness I will take it as 1 unit. Okay, for just the derivation purpose. So only I will take this as A. AB is equal to A. AC is equal to B. It's a rectangular block. Now now let us say F1 and F2 are the shear forces. So F1 is the shear force here on this edge. F2 is the shear force here. So I have written tau 1, tau 2, So tau 1 is the shear stress due to force F1. Tau 2 is the shear force due to force F2. Now we have to prove that this tau 1 is equal to tau 2. That means shear stress here and here, they will be same, equal. That is the meaning. So let us prove that. Simple proof. F1. So F1 is the force. I will take the force acting here as F1. So F1 is equal to stress into area. So we know that stress is equal to force divided by area. So force is equal to stress into area. Stress is tau 1 into area means this area I have to take. Area of CD D dash CD D dash C dash. So that area will be now, since I have taken thickness as 1, this is A. So area will be A into 1. That's what I have written here. So it becomes A into tau 1. So F1 will be equal to A into tau 1. So the force here acting shear force acting here will be A into tau 1. Similarly, I will write the shear force acting here on this edge. So what is the shear force? That is given by, once again, stress multiplied by this area. What is that area? B dash D dash D. So F2 will be equal to tau 2 into area B dash D dash D. So once again that area will be, this I have taken it as okay, this is tau 2, So tau 2 will be now, this is B, this is B, this is 1, thickness is 1. I have taken thickness as 1. So this area will be B into 1. That's what I have written. So F2 will be B into tau 2. Now, what we have to do is, next, for equilibrium of the block or the material, what happens? So here, I have to take these two. I think, can you see this? Yeah. Yeah, for equilibrium of this block, what you have to do is couple due to F1. So this is F1, this is F1. I have written stresses in the same direction, F1 will be there. In the same direction, F1 will be there. These two form a couple, as I already told. So couple will be F1 into this distance B. So you know that the magnitude of a couple is given by product of magnitude of one of the forces multiplied by the distance between the two forces. So here distance between the two forces is B. Okay. So F1 into B is the couple due to this F1, and couple due to F2 into A, because the distance between these two forces is A. So I have written that. So this is the equilibrium condition. One will give clockwise couple. So F1 will give clockwise couple. F2 will give anti-clockwise couple. They will be equal for equilibrium. If you equate these two, and if you substitute for F1 and F2, and if you simplify, this A into B will get cancelled. You will get tau 1 is equal to tau 2. So very simple proof. In the case of pure shear, the shear stresses are complementary to each other. Complementary means they will be equal. They will be equal. That is the meaning of complementary. So one set of shear force will give clockwise moment. Another set of shear force will give anti-clockwise couple. The magnitudes will be equal, because for the equilibrium of the object, when you equate those two magnitudes, you will show that you can see that tau 1 is equal to tau 2. This is a very simple proof. So the question can be asked like this: define the state of pure shear and show that the shear stresses always as complementary shear stresses. So that is the simple derivation. They may ask for 4 or 5 marks. So next, I will go to the very important concept. Next one. So I have sent yesterday the PDF of this third notes. So this we have to understand clearly, because this is very important concept for understanding the next module also, compound stresses, next module. So to understand that module also, so you have to understand this clearly. Yes. What do you mean by diagonal tension and diagonal compression? So due to that shear stress, whatever is developed, so you will be having two other forces that are going to develop within the element. So we have to understand this clearly. Please understand these sketches clearly, then it will be easy for you. So what happens in a pure shear state of an element, one diagonal is subjected to tension and other one is subjected to compression. See, this is the state of pure shear. You can write like this. If I remove that three-dimensional figure, if at all you want to show in 2 dimension, you can show like this. This is the 2D representation of that block. So I have taken toe here, same toe will act here. Here I have to take toe downwards, because this is upward, this is downward. Here this is towards right, this should be towards left. Same sketch I have shown here. The whatever earlier I explained, 3-dimensional. So this is 2-dimensional. So what is the meaning of this? This is the state of pure shear. State of pure shear which is in equilibrium. So I have taken 2 cases here. So case 1, case 2. In case 1 I have shown like this. In case 2 the only difference is I have just changed the direction here. So this toe I have taken to the left. When the toe is acting to left here on the upper face, upper edge, it should act to the right here. Okay. So similarly I have taken this downward, here upward. See here. This is upward, this is downward. All the values will be equal to toe. All these 4 shear stresses, they are equal, but see the directions. So these two, top and bottom, they are giving clockwise couple. So left and right, they are giving anti-clockwise. They will be equal. Just I showed just now that. Just now we have proved it. Here, top and bottom will give anti-clockwise. Left and right will give clockwise. Okay. Numerically, the values will be same for equilibrium. So let me take one by one. Very important. So here, when the state of pure shear is like this, when the state of pure shear is like this, okay, here what happens due to these two stresses? Due to these two stresses, what you just imagine, you can just understand this concept. These, whatever, suppose if you take this diagonal you take BD diagonal, what is the effect of these two stresses, shear stresses on this diagonal? So it will be like this. See here. So it tries to elongate this diagonal. So there will be a tensile. So tensile stress acting on this diagonal BD. You just see here. It tries to stretch like this. Okay. Then correspondingly, what is the effect on this other diagonal AC? On the other diagonal AC, it will be opposite, compression. See, I have written towards. So you know that in the last classes, I have told you that in one direction, if there is elongation, in the other direction, there will be contraction. So that is the concept we are using here. So these two diagonals, so BD diagonal, it is subjected to tension like this because of stretching in this direction as well as in this direction. This is diagonal tension. This is called as diagonal tension. Then in the other direction, automatically it is diagonal compression. So because it is called as tension because it is normal to the diagonal. See, this is shear, this is normal. That means the effect of shear on an edge will be either tension or compression on the diagonal. Please understand this. The effect of shear on an edge of a element will be either tension or compression on the diagonal. It all depends on how the shear stress will act. In the second case, you see, what I have done, I have just changed these directions. This and this and this and this, all I have changed. In this case, reverse thing will happen. Suppose if you take, so what is the effect of this? If you take this AC diagonal will be subjected to tension here. See, it is subjected to tension. Naturally, BD will be subjected to compression. So I have written sigma T for diagonal tension, sigma C for diagonal compression. Tau is the shear stress. So these are the notations. So it is very easy if you understand the sketch clearly. So this tries to stretch this diagonal and compress this diagonal. Whereas if it is acting like this, it tries to stretch AC diagonal, try to compress BD diagonal. That is the meaning. Okay. Now this is a simple proof that we have to prove that these all these will be equal. So tensile stress, compressive stress, and shear stress, all of them should be equal. That is the meaning. So you have to prove that once again using the equilibrium condition. For proving that, what you can do is you can take a simple element like this, triangular element. It is called as wedge element. You might have used that word wedge in your mechanics. Triangular element or a wedge element. Instead of going for this rectangular element or square element, you can go for triangular element. It will be easy for the derivation. So now what we have to prove is whatever tension, diagonal tension has developed or diagonal compression has developed due to the pure shear stress, all the stresses will be equal. Shear stress will be equal to diagonal tension, that will be equal to diagonal compression. Now very simple proof. What I have done is I have chosen a triangular element with sides equal. So A is this side, A is also this side. That means if you cut a square into two divisions along the diagonal, you are going to get this element. So sides I am taking AB is also equal to A, BC is also equal to A. Then this hypotenuse will be root 2A. If you take the Pythagoras theorem, root of A square plus A square, which becomes this AC length will be now root 2A. And once again, thickness I will take 1, unity. Just for derivation purpose, thickness of this element, let me take it as 1. So thickness I have to assume because I need the area. When stress is multiplied by the area, you are going to get the force. That is why I am assuming thickness as 1 here. Now let us take F as the shear force, T as the tension force. So this tension force is acting here. Please note. So this tension force is acting along this AC. So I am considering this one. So see, I am taking this element, this type. Okay, this is ABC. ABC is the triangle. So in that case, A is the edge width AB, BC is also equal to A, then AC will be diagonal length will be root 2A. Root 2A. Okay. Now this tension is acting on this diagonal AC. Shear is acting on these two faces, that is AB and BC. Now let us say take this F as the shear force. Shear force I have taken like this. See, shear force is acting downwards. This I am taking this sketch. Then one more shear stress is acting like this. So shear force is F, tension force is T. Now how to get shear force? So F is equal to, we know that shear force is equal to shear stress multiplied by the corresponding area over which that shear stress is acting. So shear stress is acting here. This F will be either you can take this or this. So F is equal to tau into what is the area of this? Area of this will be A into 1 because I have taken unit thickness. So it is A into 1. So this tau will be acting over this area. So you will be getting F is equal to A into tau. Simple expression. Now what about diagonal? Diagonal. So AC. So this tension force is acting along this area. Along this area. Once again, this area is AC into 1. So AC is once again root 2A. Root 2A. Length of AC is root 2A into 1. That becomes the area. Sigma T is the stress. So sigma T is the tensile stress, diagonal tensile stress. T is the tensile force. So force is equal to stress into area. So this area we have to take because tension is acting on this. So that means you will get T is equal to root 2A into sigma T. Now we have to consider the equilibrium of the element. So when you are taking equilibrium of this element, so I have written once again here, this T is acting like this, perpendicular to this. F is acting like this. Now we have to take both, that is sigma H is equal to 0, sigma V is equal to 0. They are the equilibrium equations. Sigma H means sum of all the horizontal forces, horizontal components should be equal to 0. Sigma V means sum of all the vertical forces should be equal to 0. Sigma M means sum of algebraic sum of all the moments of the forces should be taken about any point should be equal to 0. Of course, here we take only one condition you can take. So sigma H is equal to 0 you can take. So sigma H, to write down sigma H, we have to resolve this T into two components. We know that this angle is 45. So if you resolve this T into two components, one is horizontal component, another is vertical component. Both will be T cos 45 and T sin 45. That you know how to resolve. That you have done a lot of problems in mechanics, resolution of force. So depending on the direction, you can resolve this into two components. Now this T can be replaced by these two forces. That is the meaning. Now let us apply that sigma H is equal to 0 for this. So if you use that, what happens? F is equal to sigma H is if I take towards right forces positive, naturally forces acting towards left will be negative according to the sign convention. So F is acting towards right here, horizontal F1 is acting towards right, positive. T is cos 45 is acting towards left, so it should be negative. So F minus T cos 45 should be equal to 0. So this is the horizontal equilibrium condition. Okay. If you simplify this, you will get F is equal to T by root 2. F is equal to T by root 2 because cos 45 is 1 by root 2. So you can write F is equal to T by root 2. Now what is F? F is A into tau. We have written here. F is equal to A into tau. T is root 2A into sigma T. Just substitute that and if you simplify, you will get tau is equal to sigma T. Very, very simple proof. Okay. We are using equilibrium of the element concept. I have taken only forces acting towards in the horizontal direction and some of the forces I am taking 0. Suppose if you want to prove tau is equal to sigma C. So here I have written similarly it can be proved tau is equal to sigma C. How do you do that? For that what you have to do is you have to take the other element. Other element is this one. You have to take this one where diagonal compression is acting. See, you have to take half of this, okay, half of this, and similarly if you do, the sigma C will be acting towards towards. Then if you resolve if you apply the same method, you can do that. You can try that. So if you do that on the similar lines, instead of T acting like this, it will be downward. So compressive force will be there. So that you can call it as capital C, and that should be once again it has to be resolved into two components, vertical and horizontal. C cos 45, C sin 45 will come. So in that case also, F will be equal to A into tau only. C also will be equal to root 2A into sigma C. Instead of sigma T, you will get sigma C. That's all. Capital C is the compressive force. Here capital T I have taken tensile force, tension force, but the diagonal compression I can take capital C. So capital C will be root 2A into sigma T. Once again, if you use this concept, equilibrium concept, you can prove that tau is equal to sigma T as well as it is equal to sigma C. So this is a very, very important concept to understand even compound stresses, which we are going to deal in module 2. So what I meant to say is whenever an element is subjected to a state of pure shear, then it leads to diagonal tension as well as compression. One of the diagonals, this is only corresponding to two dimensions I am talking. So one of the diagonals, it will be subjected to tension. Another diagonal will be subjected to compression. That is the meaning. Okay. So if you can always prove that shear stress value will be equal to the diagonal tension stress as well as diagonal compressive stress. So this is the concept of pure shear or simple shear. So whenever an element is subjected to pure shear or simple shear without any normal force, then that pure shear will induce diagonal tensile stress and diagonal compressive stress depending on the direction of that shear force or shear stress. So that is the thing. So this is about simple shear and or pure shear. Now two important derivations are there. I will just explain one derivation now. You have got four elastic constants. So this is also an important derivation. Four elastic constants. They are already we have studied about all the four elastic constants. When the material is in elastic state, what do you mean by the elastic state? When you remove the load acting on that material, if it regains its initial shape and size, then we say that the material is in elastic state. If permanent deformation takes place, it goes to plastic state. So here, there are four elastic constants. One is Young's modulus, denoted by capital E, or modulus of elasticity. Another is rigidity modulus, or modulus of rigidity, or shear modulus. So there are three words. Shear modulus, denoted by G. Another one is Poisson's ratio, which is nothing but the ratio of lateral strain to linear strain within elastic limits. No units for that. Another one is K, bulk modulus of elasticity, which is the ratio of bulk stress to volumetric strain. So all these you have learned in your earlier classes. Now there is a relationship between all these four. Whenever the material is in elastic state, you can always develop a relationship between these four elastic constants. So E, Young's modulus, Newton per mm square. G, shear modulus, Newton per mm square. Mu, no units. Poisson's ratio. It can be written as 1 by m also. Then K, bulk modulus, Newton per mm square. So first E, G and K, they are in Newton per mm square. Mu does not have any unit. Now you have to understand, you have to practice this derivation because some geometry is required here, some geometrical knowledge is required. Some 4 or 5 steps are there. So first we will prove that E is equal to 2G into 1 plus mu. So this is the first relationship between the elastic constants. So this equation gives the relationship between Young's modulus, shear modulus, and Poisson's ratio. So this we will see. So E is Young's modulus, which is nothing but Young's modulus is defined as ratio of normal stress to normal strain. That is sigma divided by epsilon. Sigma divided by epsilon is Young's modulus. G is shear modulus, ratio of shear stress to shear strain, tau divided by gamma. So you should be written here. So you should know, you should be very thorough with the notations. So don't confuse. There are so many Greek letters will be there. This tau, gamma, all these are Greek letters. So tau by gamma is G. Next, mu does not have any this thing. That is a unit. It's a ratio of lateral strain to linear strain. Okay, with all are within elastic limits. Now let us see how this proof is carried out. So you have to understand. I have taken a element like this. Okay, square element only. So AB CD is the square element with edge A and A only. So A and A is the size of the edge of the square. Now I have applied a shear stress in this direction. See, shear stress in this direction towards left. So what is the effect of that? So when you apply a shear stress in that direction, its effect is it causes both linear deformation as well as angular deformation. I told that I had explained that when I explained about shear stress and shear strain. So due to this, what happens? This edge will be stretched by delta. So this is the new position. D goes to D dash. So the new position of this element, the bottom edge I have taken fixed. The bottom edge I have taken fixed, so it won't move. So there is no elongation on the bottom edge because of fixity condition. No deformation for AB, but CD will extend by delta. Okay, I have written here. F is the shear force, tau is the shear stress, so delta is the elongation. Okay, so now this C goes to C dash goes to D goes to D dash. So that means due to this force, this element is distorted. I have shown in broken line, you know. So A B C D will change to A B C dash D dash due to that force. And I have noted some angles here. Please note here. So this I have this diagonal BD will change to BD dash now. The angle between these two is alpha. Alpha will be very, very small because delta is very small. Alpha can be taken very, very small. And this angular deformation is written as gamma. So this gamma is nothing but your shear strain. I explained in the earlier class. Gamma is called as the shear strain, which is given by delta divided by A. Because gamma is equal to tan gamma. When gamma is very small in radians, gamma can be equal to tan gamma. In this triangle, tan gamma will be delta divided by A. Okay, CC dash is delta. So delta divided by A. That's what I have written here. So G is tau by gamma. As gamma is very small, gamma is equal to tan gamma or delta by A. What is the delta? Delta is DD dash divided by A. So therefore DD dash will be equal to A into gamma. Okay. So A into gamma. DD dash is equal to A into gamma. That's what is the first step. So here F is the shear force, delta is the deformation, tau is the shear stress, gamma is the shear stress. These are the notations. Now what we have to do is draw DD dash perpendicular to BD dash. So see DD dash, I have written DD dash perpendicular to BD dash. So BD dash is this elongated diagonal. So you have to draw a perpendicular here. DD dash is the perpendicular. Alpha is this angle. What is that angle? Angle D dash BD. D dash BD. D dash BD is that alpha angle, which is very small, very, very small. And beta, so beta I have taken this angle, D dash B. D dash B can be taken equal to 45 degree only because since alpha is very small, this delta will be very, very small. So you can take almost equal to 45 only. So diagonal expansion is there. Maybe slightly less than 45. You can equate it to 45 only for derivation purpose since delta is very small. The reason for this is because delta is very small, beta can be taken 45 degree only. Now consider the strain of diagonal BD. Now what we have to do is, this BD has been stretched now. What is the strain of BD? So strain is calculated using this. So increase in BD we have to calculate first. So initially BD was the length. Increase in BD, now BD has changed to BD dash. So increase in length will be BD dash minus BD double dash. The reason is since alpha is very small, this BD can be equated to BD double dash. So that is the thing here. So I written here, as alpha is very small, BD is nearly equal to BD dash. When BD is nearly equal to BD dash, BD double dash, so what you can write here is, so this BD dash, whatever BD dash is there, this minus BD double dash, that is your increase in BD. So that is nothing but D dash, D double dash. So D dash, D double dash is taken as the increase in the length of BD. What is that? From the figure, you can see that D dash, D double dash will be delta cos beta. So if you take this triangle, this small triangle, see I have shown here. So this delta, D double dash, beta is this angle. So cos beta is nothing but D dash, D double dash. Okay, cos beta is that. D dash, D double dash is cos beta. You can enlarge this triangle and you can get that. So increase in BD will be now delta cos beta. Now what is the strain? Definition of strain. Strain of BD is nothing but increase in BD divided by original BD. So change in length divided by original length is strain. Now increase in BD is delta cos beta. Just now we have proved. Divided by original BD is root 2a. What is the length of BD? Length of BD is root 2a. You can see here because these two, this is A, this is A. So diagonal length BD will be as per Pythagoras theorem, root of A square plus A square, that is equal to root 2a. So if you use that, you will be getting the strain of BD. So delta cos beta divided by root 2a, as beta is nearly equal to 45 degrees. So cos beta means cos 45, 1 by root 2. So if you substitute that and if you bring this root 2 to the denominator, you will get delta divided by root 2 into root 2 is 2a. Now what is the delta? So we have seen that delta is a into gamma. A into gamma. We have got here. See, delta is a into gamma. So delta is equal to a into gamma. See here, delta is equal to a into gamma. That's what we have to put there. Then a and a will get cancelled. So you will be getting gamma by 2. So strain of BD, you can take it as gamma by 2. So gamma is the shear strain in radians. Gamma by 2 is the strain of BD. Next, another method, another way we can